Hey kiddos, today we're going to talk about resonance. Now resonance is one of those things that there's sort of a conceptual thing behind it that gets a little bit confusing. And so we're going to break this down into 3, maybe 4 videos talking about the why, the how do you recognize it, all of those types of things. And so in this video we're going to talk about the why resonance is necessary. So line structures, remember, are sort of our shorthand way to draw what the structure of the molecule is. And a lot of times the line structure is a perfectly valid representation of what is actually going on. So we've got a 4-carbon structure here, 1, 2, 3, 4. We've got a double bond between the second and third carbon. We could then also go back in and fill in our hydrogens as well. And we would know where each of those were. So there's 3 hydrogens here. Since there's 3 bonds on each of these carbons, they each only have 1 hydrogen, and then there's 3 over here. And so we know that this is C4H8 would be that molecule. This is 2-butene is what this molecule would be. So there's no ambiguity there. That structure represents what it actually is. So let's talk about a structure where there is some ambiguity, and then we'll understand a little bit more about the rationale behind why we need to worry so much about resonance. So our primary example here for why we're going to start to get to resonance is this right here, which is called an allylic or an allyl carbocation. Okay, allyl is spelled like this. It is very similar to a vinylic or a vinyl carbon as well. So these 2 carbons here that are the ones that are actually in the double bond, those are vinylic or vinyl carbons. The carbon that is 1 removed from the double bond, so the double bond ends here or starts there depending on which way you look at it. The carbon 1 removed from that is the allylic or the allyl carbon. And so this is what we call an allyl carbocation, meaning that there's on the allyl carbon, the carbon 1 removed from the double bond, there's a cation, a positive charge on it. Okay, so great. So why does that mean resonance? Well, you might sort of, remember some of your resonance talk from Chem 1 and think, okay, well, I could probably switch where the double bond is. And indeed, that's part of what we're doing here, but it's not a matter of switching the double bond, and I want you to get a really good idea of why this looks the way that it does. So to do that, let's draw this out a little bit more. We've got 3 carbons here, right? Okay, we said that we've got a double bond between these 2. Okay, so we know that there's at least a bond between each thing here, right? So 3 carbons, that's our basic structure. We said that we had a double bond here and we had a carbocation over here, okay? So why is the resonance structure going to be necessary here? Well, to look at that, we're going to look a little bit about, if you remember some of the earlier discussions about bonding that were either in Chem 1 or maybe AP Chem or even earlier in the book that we talked about this year. Remember, the single bonds here are sigma bonds, and then we can have pi bonds that happen when p orbitals overlap sort of either this way or they overlap this way, right? So they overlap like lengthwise as opposed to end to end. End to end would be another sigma bond. So we get pi bonds then when they overlap this way. And we're going to look at them as though they were doing that. And remember that, of course, we've got sigma bonds and we've got pi bonds. So these are sigmas, single bonds there, sigmas. And then we're going to worry about what's going on in the pi bond structure because generally speaking, resonance has everything to do with what's going on in the pi bonds. So remember that your general shape of pi orbitals looks something like this. And again, we all know that I am not an artist by any stretch. And so each of these carbons has a pi bond. And remember that there are also, depending on the hybridization that's going on in this molecule, we're going this way, okay, all of that stuff. Remember that if this carbon has 2 bonds coming off of it and a hydrogen coming off of it, that it's going to be sp2 hybridized. If there's a double bond there somewhere, that this carbon is going to be sp2 hybridized. We're not going to get too much into that at the moment. But what matters is what's left is we've got these p orbitals left. Each of these carbons has at least a p orbital that's going to get involved somehow. If those p orbitals overlap this way, then that's when we're going to be able to get those pi bonds. So according to the original structure that we had there, what we were saying is that we had these 2 were overlapped, okay? And that this one was not, but instead that's where my carbocation was. Okay? But if you think about it, why could it not be, okay, why could it not be that these 2 were overlapped, right? And then the charge would have been over there. Well, in reality, neither one of those two things are really an accurate interpretation of what's going on, because if we drew this, and indeed when we drew resonance structures probably in Chem 1, you would have drawn it, there's the 1, okay, carbocation, and we would have said, hey, we got a resonance arrow here, and then we've got it going on this way, and those would have been our two resonance structures, right? But remember that neither one of those is actually what's going on. The whole reason that we worry about resonance is because any one individual line structure is an inadequate representation of what is really going on. So the question is, what is really going on? Well, what's really going on is that these three pi orbital, or these three p orbitals here, essentially provide a conduit for the electrons to flow through and to be delocalized. And remember, delocalized means that they don't belong to this carbon or this carbon or this carbon, but rather that they're flowing through these p orbitals. And remember, this is why molecular orbital theory matters to us as opposed to sort of our valence bond order stuff that we talked about before. Molecular orbitals matter because what we would essentially say is that there's one big orbital going between them that allows the electrons to move between it. And what that means is that neither that nor that is really a completely adequate explanation for what's going on. This is the closest we can come in bond line structure to say, to show this is what's going on. This is our resonance. Now, why does that happen? Well, there are a couple of reasons. So there are two things that really matter here that are why the whole idea of resonance is necessary. Remember, again, we have to resort to resonance because neither one of the bond line structures in and of itself is going to be adequate to what is actually going on. So there's a delocalization, there's the overlap of those p orbitals. And remember, it's not just the two, it's not just p orbital here and p orbital here, but there's the one over here. And so we're going to say that the electrons are delocalized. They don't belong here or even in between here, that rather they're delocalized throughout the whole molecule. And this is just the best way that we can represent it. So why does that happen? I mean, why would they be spread out? Why couldn't they just be localized and attached to each atom? Because that's obviously a lot easier. Well, so there's delocalization of the electrons because the delocalization leads to stabilization, okay? And the stabilization means that the electrons are more evenly spread then, and as importantly, the charge here is as evenly spread. Remember, a carbocation, we'll see as we do reactions throughout the course of the year, is not a particularly stable state that carbon wants to be in. That's sort of ripe for a reaction or something to go on there. And so if we can, instead of it always being right here, if we can spread that charge out a little bit, then that's a much more stable way to represent that molecule. Okay, so there are two really important points to remember, though, that for when we get the resonance here, when we're showing the resonance, when we've got two, or there could be more, there could be three structures that are the best way that we can adequately represent what is actually going on in the molecule with our inadequate bond line structure. So the first thing to remember is that there's not a flipping back and forth. So one of the foremost, misconceptions that students tend to have about this is that when we draw this, is that what we're saying is that sometimes it's in this state and then sometimes it's in this state, and it's sort of like oscillating like in a wave-like pattern back and forth. That is not true at all. There is no flipping back and forth. It is never in this state or this state, but rather it's an amalgam of these two things. It's a blending of these two things together. Okay? So it's this way sometimes, or it's this way sometimes. It's not like there's a quantum shift or something there going on that we're trying to figure out which one it is. Rather that it's a blend of those two things together. So that's the first thing. There's no flipping back and forth. Okay? And the second thing to remember here that's really important is that it's not something that's happening to the molecule. Again, if it's not flipping back and forth, that means resonance isn't like something that's going on. Resonance is our way to express in a bond line structure what is actually going on in the molecule. And remember, our bond line structures are sort of set up and predicated around the idea of normal valence structures. And of course, things are a little bit more complicated than that. If we threw molecular orbitals and all that in there, then everything gets a little bit more complicated. So it's not something that's happening. Resonance is something that is. It is a resonance structure. It's not a structure that is undergoing resonance. Okay? So that's part one of the video, and we've got a lot more to talk about resonance, but hopefully that gets you a little bit better idea of the what is resonance. So thanks, kiddos.